Hi everyone, here we're going to discuss the theory behind the Archimedes principle lab. And the Archimedes principle is based on this idea that if you have a tank with some water, and if you toss a ball into the tank and the ball floats, well, first, water is going to have a density, rho W, which is going to be equal to 1,000 kilograms per cubic meters. But if there was no water, the weight of the ball would make it fall down to the floor. But the ball floats, and the only way that that's possible is if there is another force that balances out the weight. And that force that makes it float, we're going to call it the buoyant force. I'm going to call it F sub B. And so that's going to be the buoyant force. So this is the force that we're going to investigate today. So in the first case, the buoyant force, there's going to be two equations. The buoyant force can be defined as, it's going to depend on the liquid that the ball is submerged in. So in this case, it's going to depend on the density of water. And the buoyant force, it's counteracting gravity. So the buoyant force is also going to be proportional to gravity. And besides that, the buoyant force is going to depend on how much of the ball is underwater. So it's going to depend on the volume submerged. So this is going to be, this is the basic definition of buoyant force. But there's another way that you can calculate the buoyant force as well. So if you have a tank with water, and you can weigh the object in air, so you can get the weight of the object in air, Fg air. And when you dunk it into the water, its weight is still present, Fg air, but because it's in water, there's going to be it's submerged in water, there's going to be a buoyant force that's going to push upwards. So because of that, when this object is submerged in water, it's going to weigh less. So the weight when it's submerged is going to be less than the weight when it's in air. And from that, we can also get another equation for the buoyant force. So the buoyant force is also defined as the weight of an object submerged in air minus the weight of an object submerged in water. So these are the two equations that we'll be verifying for today's lab. So this equation is going to relate to part 1 and part 2 of today's lab, and this equation is going to relate to part 3. So let's look at part 1 and part 2. So for part 1 of today's lab, you're going to have a tank of water. And what you're going to do is you're going to weigh, well, there's going to be a mass. And the mass is going to be connected to a force meter that's going to read a force. So it's going to read the force while it's in air. And what you'll do is that you'll dunk the mass into, it's going to be a bottle. So you'll dunk the bottle into water. And again, you're going to read the force reading when it's submerged. And from there, you'll be able to calculate the buoyant force. But there's a few things. So this, in the simulation, what you'll be able to do is that you'll be able to change the mass, make it more massive or less massive. And the other thing that you'll be able to change is how big the bottle is. So you'll have a small bottle, but you can also increase the bottle to make it bigger. So that means that you'll also be able to vary the volume of the bottle. So from there, you'll have a table. And a table is you'll be able to record the mass of the bottle, the volume of the bottle, and these force meter readings here. The force when it's in air, and the force reading when it's submerged in water. And so for part 1, you're going to keep the volume constant. So what you'll do is that you'll change the masses, and for each mass, you're going to record the corresponding weight in air and the weight submerged. And again, for each mass, you're going to record the corresponding weight in air and the weight submerged. And from there, you'll be able to use this equation to calculate the buoyant force. Part 2 is similar. The only difference with part 2 is that the mass is going to stay constant, and what you'll do is that for the masses, you're going to increase the volume. You're going to make the volume bigger and bigger. So for part 2, the mass is going to be constant, and you're going to vary the volume. So that means that for each trial, you're going to change the volume, record the weight in air and the weight submerged, make the volume bigger, record the weight in air and the weight submerged, make the volume bigger, record the weight in air and the weight submerged. And again, you're going to use this equation as well for part 2. So part 3 is going to be the second equation. So in part 3, we're going to verify this equation, that the buoyant force is equal to, I'm going to rewrite this equation. I'm going to rewrite this like this. So the buoyant force is going to equal gravity multiplied by density times volume. Because this way, this is going to have the form y equals slope times x. So what this means is that for part 3, you're going to plot buoyant force versus density times volume, and when you do that, you'll get a slope, and the slope of that line is going to correspond to gravity, 0.81. So let's see a little bit more about how this experiment is going to work. So you're going to have your tank of water, and again you're going to have your mass in air, and the force meter is going to read the force while it's in air, and you're going to dunk it into the water, and the force meter is going to read the weight of the object submerged in water. For part 2 though, each trial you're going to vary both the mass and also the volume. So you're going to make the mass bigger and also make the volume bigger for each trial. So in part 3, the table is going to look like this. You're going to have a table for a slot for masses, slots for volume, and from the volume you'll also be able to calculate density times volume, and you'll also be able to calculate the buoyant force. And so once you've gotten those terms, then what you'll do is that you'll plot buoyant force on the vertical axis, density times volume on the horizontal axis, and that's going to give you this graph here, where you'll have buoyant force on the vertical, density times volume on the horizontal. You plot that, you get a slope, and a slope is going to correspond to gravity, which verifies this equation. Buoyant force is equal to G times rho V. So this completes the theoretical explanation for the Archimedes